Welcome to Study Loop.
Hi everyone, thanks for joining me today. So what we have is a problem that is looking at the concept of work kinetic energy and tied in with some circular motion concepts. So what we have is we have this mass that is moving to the right at a velocity v and going over a spherical or cylindrical structure, BCD. And what we're asked to find is the theta, the angle at which the mass leaves the surface BCD, and also finding the x distance from where the mass leaves the surface and hits the ground. So what we're going to do first is find the angle at which the theta leaves the surface. So what we're assuming here is that at this angle, the mass barely contacts the surface, so only the weight is actually acting on the mass itself. So we're going to go ahead and draw a free body diagram of this mass at that theta. And this is the surface here, and what we have, or we'll draw the surface here, what we have is a weight force acting, we have a weight force acting straight down, and then we have a normal force acting away from the surface. And if we draw our coordinate system, we can see that the normal direction, it lines up directly with the normal force, and the tangential direction is directly perpendicular to that, so normal, tangential. Now, as we resolve our forces, we'll see that the components of weight, which I will draw here, this is our theta, and just by a triangle, we'll see that that same theta is right here. And we'll see that in the normal direction, the only force that we have acting is the component of the weight force, that is cosine theta. So we'll say that W cosine theta is equal to ma. And in the circular motion nomenclature, that is equivalent to saying mv squared over h. So we're going to go ahead and plug in for w, which we know to be mg. So we're going to say mg cosine theta equals mv squared over h. We can cancel out the m's, and we'll find that v squared is simply equal to gh cosine theta, and that's v squared. And we'll see why this comes in handy later on. Next, what we're going to do is look at our kinetic energy and works. So we see that at B, we only have kinetic energy, so that's 1/2 mv squared. At the point at which the mass loses contact with the surface, we're going to call that T theta L, which I'm going to signify as theta leaving, is equal to another 1/2 mvf squared. Now, the work is going to be simply from the force of gravity. So we're going to go from B to theta L. Now we're going to see that's the force of gravity times the difference in heights. And just to draw a small triangle here to show we're starting at height h, and that's this point shown here. That's this point shown here, and this is going to be theta L, the point theta L where the mass loses contact. And this is the angle theta, similar to here, angle theta. So we see that the difference in height is this guy, and this is h. So, and because this is the radius, this is also going to be h. So the new height is going to be h cosine theta, and that is what we're going to do here, minus h cosine theta. So we know that the kinetic energy at the beginning added with the work from B to theta L will be equal to the kinetic energy at theta L. Plugging in for these things, we know that kinetic energy at B is 1/2 mv squared plus the work, which is mgh minus h cosine theta, is going to be equal to 1/2 mvf squared. Now, we explicitly do not know Vf, but we do know Vf in terms of the rotational motion, and that is right here. So that's where this comes in useful. So we'll go ahead and plug that in, and what we get is v squared over 2 plus gh 1 minus 1 cosine theta is equal to hg cosine theta over 2. Continuing on, we're going to expand what's in the parentheses, v squared over 2 plus gh minus gh cosine theta equals GH cosine theta over 2. And now let's go ahead and combine like terms. V squared over 2 plus GH is going to equal 3GH over 2 cosine theta. And then we're going to bring that 3GH over 2 to the other side. So we're going to see that V squared plus 2GH over 3GH is equal to cosine theta. Now we know what the initial velocity is. It's 8 feet per second. We know that G is 32.2 feet per second squared. And we also know what H is. So this is a simple inverse. By taking the inverse of both sides, we can see and we find that theta is equal to 27.4 degrees. And that's theta L, which is the angle at which we lose contact with the surface. Next, what we're going to do is we're going to find the distance x from where the mass loses contact with the surface and comes to hit the ground. So we're going to find delta x. So what we're going to do first is we're actually going to plug in the theta that we found to solve for the velocity at that point. Now if you recall, the velocity is given by hg cosine theta L. And Vf is equal to hg cosine theta L, the square root. As you might also recall, the height at which we lose contact is going to be h1, and that's going to be equal to h cosine theta L. Now just using our kinematic equations, we can say that the height at which we lose contact is equal to Vf sine theta L t, which is the vertical component of velocity times time, plus 1/2 at squared, which is due to the acceleration. So now what we can do is we know h1, we know Vf, we know theta L, and we know acceleration. We can solve for t, and we see that that is 0.295 seconds. Now what we can simply do is just use kinematic convention and say that at the point of contact in unrestricted free motion through gravity, the horizontal velocity will be constant. So we can solve for a distance d from the point of contact to the point of contact with the ground, and that's going to be Vf cosine theta L times t, which we find to be 2.42 feet. Now the final distance x is going to be is going to include this distance d, but is also going to include h sine theta L, which is where the mass encounters point B. So the sum of this is 3.81 feet, and this is our x. Final answer.